Hello, this is Rhys Harris with the director's cut for the Playbook for Radical Functions standards. Again, definitions and theorems. You could easily do a word wall to cover the basic definitions and theorems, make it if you have a class incentive program, students can do it on yourself, you could check off and they'll get there. This is essentially direct instruction, giving them the basic formulas, showing them what it is. And this is a very good site found by my group mate, Precalculus, Power and Radical Functions. So it connects and bridges from power to radical functions. Wrong side. Okay. The good thing is it's an actual video along with visuals, so it can model what to teach. If you're a new teacher, it can show you what to do, how to do it. You can even play. It's only 10 minutes. And it covers those bases to give the students some foundation, because essentially the big ideas they build, one, you can't get to 6 without starting at 1. Solving rational equations through Desmos, letting students visually, using technology, practice solving. Seeing that solving radicals is different from solving quadratics or power functions. Common error, using the big ideas, where students are put in peer groups, and they're asked to, and the good thing with this that my group mate did was you solve it, you turn it in, the teacher hands it out to other students, they assess it, evaluate it. It's less stress because it's not a full-on quiz grade unless you make it so. Students can think they got it right, but then perspective from another peer is always very helpful. And you can even use previous year's work to model and show this is a good way to make corrections using care and concern versus an unproductive way. When you look for errors and issues, you're really helping your peers out and vice versa. 3 examples of very Algebra 2 level appropriate problems. Making the case, connecting from reality to mathematics. Big ideas, very good application problem. You can look and see, oh, radical function doesn't have the radical sign, but oh, that's another way. So it's a good way to link into review. Why am I doing this? It's often good to mention things that you would have in this level 3 and level 6 with big ideas at the beginning to sort of hook them. This is why you have to go through 1 and 2 to get some skills so we can apply things. And this is why we need this to function in society. Mathematical vision. Part 1 is a discussion platform to help students essentially discover and find their own light bulb moments and make connections, connecting the Pythagorean theorem. We have things squared, this is square root, connecting what we did previously. There's something involved between solving. We use radicals or square root at least to undo squaring, vice versa. Additionally here, we're gonna use an activity where it's, we're gonna use Desmos. It would be best if students had their own Desmos. Or if they're in groups, at this phase, I'd rather individual work because in one of the sources you posted practices with Margaret Smith and Mary Kay, I believe on page 104, it said initially when students are first learning things, give them time to do it on their own before you throw them in groups. I would prefer individual. If it is Desmos, encourage students to individually work on their calculators and then toss them with their peers if they can share a computer for Desmos. They do have a Desmos app on their phone as well, but that's an administrative issue if you can use it or not. You're essentially dropping Easter eggs. Easter eggs I use are ways to describe sneak peeks for upcoming things, things they've seen previously. This is set up like the Pythagorean theorem. Graphing this on Desmos won't work for a calculator. If they do try to graph it in their calculator, it's a very good learning opportunity. Graphing this in Desmos, graphing this in calculator and Desmos, and comparing and contrast. Why can I graph this versus not that? Only 5-minute video, so I have to move along. Also graphing this and seeing that's only the top of the circle, not the bottom of the circle. Moving on, a very good review of when we solve radicals, it's plus and minus. Square root of 36 is 6 or negative 6. Throwing in that negative sign shows, oh, there's the bottom of the circle, light bulb moments go off. So hopefully as they see equations like this, they will have an idea of what's going on, what the graph looks like without having to actually solve it. Moving on, quadratics, radicals, graph that, see that they're symmetric in the diagonal line. They actually see it. Cubics, they actually see it. They do the trace feature in Desmos of their calculator. They look at the coordinates. either using this as a crutch or on their own, if they see this is squared or not, literally writing the coordinates, reversing the coordinates, writing, reversing. Hopefully they get to the point where they don't have to look at the graph, they could just do it. Practice directly connecting linear functions to solving for an inverse individual by hand, using the same steps, writing out the coordinates. When we graph, we realize the coordinates are reversed. The whole point of this is to get them to see that when you reverse the coordinates, you have to change the function. Switching out x and y and solving for y is the same thing. It results in switching the coordinates on the graph, and that's why it's reflected over that diagonal line. And then getting students to write rules, creating their own rules. At the end, when they're done, you can then post rules and they can compare and contrast. But getting them to come up with their own rules before giving it to them helps them create, and when they create, they can see. Part two is extra additional practice if needed. Solving situations about radicals. You have to monitor and adjust your own students, but this sort of solidifies and gives them opportunity to practice the same skills we developed in this class discussion, using matching cards. And if even no more practice is needed, guided notes in class. These are options. Because once you get past math voice, math vision, the voice and the dialogue is really like, you really need to be on your game. So make sure you try to catch them before you get to this, if possible. Because nothing's worse than doing an activity, but not really getting why you're doing it. You're just doing it because you think it's fun. But this is a nice activity. I know I'm over my 5 minutes. Creating and building so they could discuss. And when I say discuss, in this case, they are writing, because we're not at the debate stage. If they are discussing instead of writing, it's simply stating things I agree. I'm not looking for a debate. I'm not looking for a why yet. It's, do you agree? Do you not? And this is where you're going to the teacher more. We have a difference of opinion, help us out. The next stage with discourse or dialogue is when they try to hash out and come up with their own reasons instead of relying on the teacher. Very good activity, simple, lots of prompts to respond to. You could do this as a dialogue. I don't want to be so stiff where it has to be written. There's a difference between developing a voice when you're talking versus a complete dialogue. This isn't give and take. This is, I think it's this. And then you're asking for feedback and a response. And then the teacher is much more involved in the dialogue. But it literally leads them to seeing how do we describe how we increase the strength of an electromagnet? Do we increase the voltage or do we increase the power by increasing the number of coils? I have to move on. Constraints are listed. This is a good opportunity to move into dialogue, where as you're working through the next unit with dialogue, students can write their own interview questions, and you can use this website to interview a scientist about electromagnetism and all that. Another way of viewing dialogue other than just between your peers. This is an activity, different approaches to radical functions. Students discuss what's the best way to approach it, analytical, numerical, looking at the functions and the graphs. You're forced to refer back to steps 1 through 5 to help you answer this. And then a good extension activity, taking things further from big ideas where you're using radicals to solve creating a spiral, comparing the wheel or the spiral of Theodorus to the golden ratio logarithm. It's a good segue into logarithms as well. Logarithms are the inverse of exponential functions. All that stuff. Brain teasers are there. I know I'm over. I'm sorry. I'm stopping. Thank you. I need to stop recording.